Welcome to my channel Physics with Akash Goel. In this lecture, I am going to take next topic of semiconductor, which is logic gates. Signals are of two types. Electrical signals are of two types. One is called analog signal, another signal is called digital signal. What is analog signal? It is a signal. Signal means voltage or current. It is a signal which continuously varies. It can have continuous range of values. Just like for an example, sinusoidal voltage, you can see in this graph the values are continuously varying values, continuous variable values. What is digital signal? A signal which can have only two discrete values, just like in this graph we can have this value or this value, we can have this or this. So these are the two possible values only. The semiconductor devices, which consist of diodes and transistors, can be designed for two-state operations. What are those two states or two value operation? As we have studied in transistor chapter, transistor lecture, if we operate transistor in two states, which is saturation and cutoff, in saturation and cutoff, voltage is either low or high. So these are the two states, two discrete states. In these states, output voltage can have only two states or two values. The values are either low or high. The exact value of voltage is not very important if the voltage is distinguishable as low or high in digital circuit. Digital circuit is an electronic circuit which is designed for two-state operation. So it is a kind of circuit, electrical circuit, which is designed for two-state operation. What are those two states? Two states are either low or high. The output voltages of digital circuit is either high or low and no other value. There is no value in between. It can have only two value, high and low. These states can also be expressed as on and off. So we can say that it is operating in two states. One is on, another is off, or we can assign some digits to it. For on we can assign 1, for off or low. For off or low we can assign it 0. The numbering system that uses only 1 and 0 as digits is known as binary system. So in binary system we use only two digits, 1 and 0 only. So now what are logic gates? It is a digital circuit with one or more input signals. So we can have one or more input signals. Input signals means input voltage or input currents, but it can only have one output signal. So this is called logic gate, because in logic gates we have logical relationship between input and output. There will be a relationship between input and output there, and this relationship will be based on some logics. So that's why it is logic gate. The operation of logic gate may be described either by truth table. So what are those logical relationships? Those logical relationships we can describe them using a table known as truth table. We are going to see this further. Or we can use Boolean algebra. So Boolean algebra or truth table, these are the two ways in which we can describe the operations of logic gate. There are three basic logic gates. One is called NOT gate, OR gate and AND gate. So these are the three basic logic gates. Now let us take NOT gate. NOT gate in circuit we show this by this kind of symbol. A is the input and Y is the output signal. So A denotes input and Y denotes output. What does this do? This gate inverts the signal, just it reverses the signal. In Boolean algebraic notation, we represent this Y as Y is equal to A bar or A prime. So Y is A prime or A bar. Truth table, this truth table will give the relationship between the input and the output signals. If input signal is low, 0 means this is low, then output signal will be high. It just reverses the input signal. If input signal is high, then output signal will be low. For an example, we can use this kind of circuit to illustrate NOT gate. Suppose this is some voltage source, this is a bulb, and here is a switch. And if switch is off, we denote this state by 0. If switch is on, that means switch is closed. If switch is closed, we denote this by 1. If this is off, that means it is open, then bulb will glow. So bulb is on and we are denoting this state of bulb by 1. If this is closed, that means switch is on and this is 1. If this is closed, then this will be a short circuit and no current will pass through this bulb, so this will be 0. So for 0 it is 1, for 1 this is 0. This is exactly not the example of a logic gate. From this example I am just illustrating the operations. This operation is resembling the inverting the signal operation which is performed by NOT gate. Normally gates are made up of some semiconductor, diodes or transistor. So diodes and transistor are used to make logic gates. So this is just for illustration. This process also resembles the NOT gate operation. NOT gate with transistor. We can use transistor to make this kind of NOT gate. We have already seen this kind of transistor, common emitter configuration, in which we have seen if input is low, then output is high. If input is high, then output is low. If you operate transistor in saturation and cutoff region, the transistor operates in cutoff region when this input is not properly forward biased, and transistor operates in saturation region if this output is not properly reverse biased. So we have already seen this kind of thing in transistor. So when V input is high, V output is low. When V input is low, then V output is high. So this is NOT gate using transistor. Sometimes we represent the operation using some graphs, which is also known as waveform. Suppose this is signal A, this is high, this is low, this is high. When this is high, this output is low. When this is low, then this is high. When this is high, again this is low. So it just inverts the signal. Next, let us take AND gate. AND gate has symbol like this. It has two inputs, A and B are two inputs, and Y is the output of this gate. And in Boolean algebraic notation, Y is equal to A, Y is equal to AB, Y is equal to A into B. It gives high output when both are high. So the truth table will be like this. When this is low, obviously this is low. When this is low and this is high, then also it is low. It will give high output when both are high. So when A and B are 1, then Y is also equal to 1. For circuit resemblance, these are two switches, and if we close the two switches, then only this bulb will glow. If one of the switches is open or both switches are open, then the bulb will not glow. So it resembles the operation conducted by AND gate. AND gate using diodes. Suppose these are two diodes and these are two inputs. A and B are two inputs. Input voltage will be there, A and B, and this is earth and this is 5 volt. 5 volt is just resembling the high voltage, and at this point the output is taken, and this output is denoted by X, and which is X is equal to A and B, and is operation. So we can write AB or A and B. We can see how this system resembles, or this operation is AND gate, how this is AND gate. Let us take A as 0. If I take A as 0, then this is the low voltage, and this diode will be forward biased, because if A is low voltage and it is connected to N side, then this diode is forward biased. So if A is 0, then D1 is forward biased. If B is 1, then this D2 will be reverse biased, because this is at higher potential and higher potential is connected with N. So this will be reverse bias in this case. If this is forward biased, then this will conduct. So this will conduct, and if this has 0 and this is conducting, so it all becomes just like a conducting wire. I am assuming resistance to be 0 for ideal diodes. So this is 0, so this will also be 0 because this all is conducting, and here we can reach here also, and this will be 0. So this is 0, this will be 0, this is 0, and this is 0. So from this I am reaching here, and this is 0. If both are 1, suppose if both are 1, this is 1 and this is 1, so both will be reverse biased. There is no conduction, there is no conduction of electricity from here. So this is reverse bias, and this is also reverse biased. There is no current here. If there is no current here and here, obviously there is no current here, there is no current in this resistance. If this is 0 volt and we have battery of high voltage, this is 5, so this will also be 5, and this is again 5. Obviously this will be high. So if both are 1 and 1, so this is also going to be 1. So obviously this gate is AND gate. Next I'm going to take OR gate. In OR gate, this is the symbol of OR gate, and in Boolean algebraic notation we can write y is equal to a plus b. It gives high output when any of the two is high. So if a is 0, b is 0, then only it is 0, otherwise it is 1, 0, 1, this is 1, 1, 0, this is 1, 1, 1, it is 1. And for circuit example, if any of this switch is closed, then this bulb will glow. And using diodes we can also see this. So if a is 0, suppose if a is 0, then this 0 is connected with p, so it is reverse biased. If b is 0, again this is reverse biased, both are reverse biased. There is no current anywhere here, and obviously there is no current here. This is 0, so obviously this will also be 0, so it is completely 0. So 0, 0, and this is also 0. Suppose if a is equal to 1, so if a is equal to 1, this is forward biased, and if this is forward biased, this all becomes conducting. This diode becomes wire of 0 resistance. So this is 1, and this will also be 1, and this is 1, this is 1, and this is again 1. So it is OR gate. After basic gates, I am taking next as JOR gate. So it is XOR, and this is also called as exclusive OR gate. So this is exclusively OR gate. How it is exclusively OR gate? It gives high output if one and only one input is high. If both inputs are high, then it is not going to give the high output. It is the symbol for this, and in Boolean algebraic notation it is equal to this. This is a b bar plus a bar b. And how do we make this gate? We can make this gate using basic gates, and to make this gate we are using this kind of system. First we have to make a b bar. So suppose this is a, and this a is fed into this AND gate, and suppose this is b, and this b is fed into this NOT gate, so it is b bar, and this a and b bar are now fed into this AND gate, so it will become AB bar. Now let us make A bar B. So first A is fed into this NOT gate, it will give A bar, and now B is fed into this, so A bar and B are now fed into this AND gate, so it will give A bar and B, A bar and B, so it is A bar B. Now this two, there is plus means OR, so plus represents OR gate, so we need OR gate, and in OR gate we are feeding these two values, AB bar and A bar B, and this will give us AB bar plus A bar B. We can also write a truth table for this. So I have written all the values in order. First I have written A and B, then A bar and B bar, and then AB bar. For example, A B bar, if A is 0 and B is 1, so AND of AB, A and B bar, obviously this will be 0. Likewise I have calculated A bar B, and for these two columns you can just find the OR operation between these two. 0 0 it will give 0, 0 1 it will give 1, 1 0 it will give 1, 0 0 it is going to give 0. So it is giving 1 when this or this is equal to 1. If both are equal to, if this or this equal to 1, if both are equal to 1 or both are equal to 0, then it is not going to give the high output. It will give high output when only one of them is 1, otherwise it is going to give 0. Next, universal gates and NAND gate and NOR gates. NAND gate and NOR gates are called universal gates because using these two gates we can make any gate. By repeating these gates we can make other gates. What is NAND gate? So NAND gate, it has two words, one is N and another is AND. This N represents NOT, so this is NOT AND gate. So how do we calculate this? A and B are two inputs, and first we have and there is a circle here, and whenever this circle comes it represents NOT. So first you take the AND of A and B and then take the NOT of it. So AB bar, AB is AND A and B, and then you are taking the bar. So Y is equal to AB bar. So this is the symbol. Truth table, so you can easily draw the truth table and see this. So this will give 1 if both are 0. If one is 0, another is 1, one is 1 0, 1 and 0. If both are high, then it is going to give the output as low. So if both are high, so it will be low, and in all the other cases it is going to give 1. So it is just opposite of AND gate. AND gate gives a high output when both are high. It is giving low output when both are high. So it is just opposite. Obviously it is a inverted gate of NOT. It is inverted gate of AND. AND is inverted and this is not AND. Next is NOR gate. So likewise this is not OR. So first you take OR and then NOT is applied here. So this is OR and this is NOT. So first you take the OR and then you take the NOT. So A plus B bar. Again you can draw the truth table. It will give the high output when both are low. If any of the two is high or both are high, then it is going to give the low output. Basic gates from universal gates. As I said, we can make several gates, other gates from using this NAND gates. So let us first take the NOT gate from the NAND gates. So this is the NAND gate, and I am feeding two inputs and both the inputs are equal to A. So this is A and this is A, and first these are passed through this AND gate. So A and A, obviously it is equal to A, and then there is a NOT. So A and then there is a NOT. So this is A bar. AND gate from the NAND gate. So A and B, first it is passed through this NAND gate. It will give AB bar. And again if I apply a bar here using this NOT gate, so AB bar, then again a bar, so it will give this AB. It is simple like this. If this is A bar and I apply a bar again, so it will again become A. So AB bar and again a bar over it, because this is a NOT gate and this NOT gate is taken from this first operation. So this is AB. OR gate from NAND gate. To make OR gate we use this Boolean algebraic relation. This is A bar B bar whole bar. So A bar and B bar whole bar. In Boolean algebraic relation, this can be proved that it is equal to A plus B. We should directly remember this relation. So to make OR gate, we will use this operation, and using this operation we can say that if we are able to make this kind of system, then this system is equal to A plus B. So how to make first A bar? So A, this is NOT gate, so we will get A bar. B, this is again NOT gate, we will get B bar. Now we have to get the AND of it, A bar and B bar, and we have to apply a bar again. So it is to pass through this NAND gate. So this NAND gate will do A bar and B bar and whole bar. So, and from this Boolean algebraic relation, this is equal to A plus B. We can also verify all this from this truth table. If nothing strikes in our mind, we can verify all these facts from truth table. So you can see, if you take A as 0, B as 0, then this is 0. If you take any of this A and B equal to 1, then you are going to get 1 here. Next, not using NOR gate. Now using NOR gates, we can also make some other gates. So NOT gate using NOR gate. So A is fed into this OR gate. So A or A, this is again A, and there is a NOT here. So from this we will get A, and this NOT will invert this, and we will get A bar or A prime, not A. OR gate using NOR gate. So first, from this operation, what we can get, this is a NOR gate. So this is not OR. So this is A plus B, and there is a bar over it, and again this is a NOT gate. So A plus B bar, and then again a bar. So bar will be removed, and this will be A plus B. AND gate using NOR gate. So AND gate using NOR gate can be realized using this Boolean algebraic relation. This Boolean algebraic relation says A bar plus B bar whole bar, this should be equal to AB. So we are going to perform this, and we will say this is equal to AB. So first make A bar. So this is A bar or A prime. This is again NOT gate. This will give B prime, and this A prime and B prime, we have to take OR of it, and they take the NOT of it. So first OR, then NOT. So this is A bar plus B bar whole bar, and this will give us AB. Now let us see some Boolean algebra theorems which will help us in solving some problems. This is A plus 0, and this is going to give us A. Suppose A is 1, then obviously 1 or 0 will give us 1. Suppose A is 0, then 0 or 0, plus means OR operation. So 0 plus 0, 0 or O, obviously this is 0. A and 1. A and 1 is also giving us equal to A. Suppose A is 0, so 0 and 1, obviously this is 0. 1 and 1, obviously this is equal to 1. A plus A bar is equal to 1. Suppose A is 1, then A bar will be 0. So 1 or 0, this is equal to 1. Obviously both will be opposite. If this is 0, then this is going to be 1. So obviously this is equal to 1. A and A bar, obviously if this is 1, then this is 0, obviously it will going to give 0. It is 0, then this is 1. So this AND operation will always give us 0. A or A, obviously this would be equal to A. If this is 1, so this will also be equal to 1. So 1 or 1 will always give us 1. So all these things can be easily verified. A and A, obviously this should be equal to A. A plus 1, that means A or 1. So 1 is always here. So if we perform OR operation on this, we will always get 1 here. A and 0, so 0 is here, and this AND operation is 1 when both are equal to 1. So this cannot be equal to 1, so this is always equal to 0. A bar, then again a bar. So 2 bar will make it bar free. It is equal to A only. Let's take some more theorems on Boolean algebraic operations. A plus B is equal to B plus A. Yani A or B is obviously equal to B or A. This is commutative. A and B is obviously equal to B and A. It makes no difference which is first and which is written after. A plus B plus C. So it can also be written as A plus B plus C. A and B and C. So it can also be written as A and B and C. A and B plus C. So it can be multiplied like this, A and B or A and C. This plus represents OR and this dot represents AND operation. So again A plus B and C plus D. It can also be written A and C, A and D, B and C, B and D. So it can be written like this. So this is called as distributive law. We can distribute A plus AB. So A plus AB, this is equal to A. Be written like this, A into 1 plus B, and this 1 plus B is obviously give us 1. So this is 1, and A into 1, A and 1, A and 1 will give us A. Now in the last we have two very important theorems which are known as De Morgan's theorems, and we have already seen these two. So this is A plus B whole bar. This is going to be A bar and B bar separately. We can also write this slightly in the different manner, A bar plus B bar whole bar. So what are we doing here? This A is now with a bar, B is now with a bar. So this A bar will have a bar again and it will become A, and this B bar will have a bar again, it will become B. If here we are having a plus, so here we are having a dot or multiplication, or we can say here we are having OR operation, here we have AND operation. So this is OR and it is converted to AND. So next is AND and it will be converted to OR. So this is AB whole bar. So this will be A bar plus B bar. Again we can write it in some different manner. This is A bar dot B bar and whole bar. So again this A bar will have a bar again, it will become A, and this B bar will have a bar again, it will become B. So here it is AND, here it is OR. So these theorems are very, very important in solving several problems. In solving problems we can use truth tables, or sometimes we can use this Boolean algebraic theorems, and using this Boolean algebraic theorem sometimes calculations are much less. Let us take a question. To get output 1 at this R for the given logic gate circuit, the input values must be. So one method can be, we can check all these options and easily we can do this problem, and other is we can draw the truth table for this operation, and by drawing truth table we can easily see which is the suitable option, or if possible we can use the Boolean algebraic relations and from there we can easily do this problem. So this X is passing through this NOT gate and it will give X bar, and in this gate X bar is fed, and from here Y is coming and this Y is fed into this, and this is OR gate, and from here we will get X bar or Y, that is X bar plus Y. For this operation what is coming here, so X is coming here directly and this Y is passing through this NOT gate, so this will become Y bar. So X and Y bar, and all this is passing through this NAND gate, so this is a NAND gate here, and from this NAND gate we will get AND of it and bar on it. And using De Morgan's theorem, using the Boolean algebraic relation, we can also write it like this. This AND is can be converted into OR, and this X will have a bar now, and this Y bar will have a bar now, and Y bar having a bar will be bar free. This is X bar plus Y. We can easily see this P is X bar plus Y, and this Q which is fed into this is also X bar plus Y. So these are the two similar inputs. P and Q are the similar inputs, and if P and Q are the similar inputs, and this is suppose let's say this is Z and this is Z, so Z and Z, so first we have to take OR, Z or Z, Z or Z will give Z, and there is a NOT here, so it will give Z bar. And what is this Z bar? this is x bar plus y whole bar. Again we can convert this in AND operation, and this x bar will have a bar, so it will become bar free. This y will have a bar now, so this is finally x y bar. So result of this is R, which is x y bar, and this R should be 1, and this is AND x and y bar, and this should be 1, and this y bar should be 1, and for y bar should be 1, y should be equal to 0. So 1 and 0, so x is equal to 1, y is equal to 0 will give us R is equal to 1. So option 4 is correct. Next question. This A is fed into this will become A bar, this B is fed into it, this will become B bar, and this A bar and B bar are going through this NAND gate. And what will this NAND gate will do to these two? So A bar, B bar and bar over it, and it will become A bar and another bar will make it bar free, B bar, another bar will make it bar free, so this will become A plus B. So this Y is now A plus B, and this A plus B is obviously the OR operation. Next question. So in this question, again this kind of situation is given, and we have to find this output in one of these options. So one thing is we can make the truth table and verify which option is going to be correct, and we can also use the Boolean algebraic relation. So this A is fed into this, and this B is fed into this, and this is a NAND gate, so it will give AND and bar over it, so it will give AB bar. What is fed into this gate? This is again a NAND gate, and A is coming over here, and this AB bar is going over there, so this will take AND of it, AND of A and AB bar, and again there is a NOT at the end. So what is this going to give us? A and AB bar and whole bar. This is OR gate, so what is going into this? This is AB whole bar and B, so this will give us the AB bar plus B. Now I can use Boolean algebraic relation on this, and this AND which is coming here can be converted into OR. So how do we do this? This can be done like this. This A will have a bar now, and plus AB bar and again a bar. So AB bar again a bar. So there will be 2 bar here. So A bar plus AB. So this can also be written as A bar plus AB. Now this and this are fed into this NAND gate. So this and this we have to take the AND of it and then place the NOT on it. So some kind of heavier expression will be like this. This is AB bar plus B. Take the AND of it first. This A bar plus AB, and we have to take whole bar over this. Now this AND we can convert into OR. So let us put a bar over it. AB bar plus B and whole bar plus A bar plus AB, A bar plus AB and a bar over it. Now we can again use the Morgan's theorems, and this plus can be converted into AND. So AB bar and a bar over it, so it will become just AB and it is B bar plus, again apply on this, so it will become A bar and bar, so it will become A, and this is AB bar. There is a theorem A B dot C, we can also write it as A dot BC. So from here we can write A dot B bar. and this can be written as a dot ab bar can be written as a bar plus b bar. So what is b and b bar? Obviously this is 0. There is if you take AND of b and b bar, this is 0, and a and 0 will also be 0, plus this can be written as a bar plus ab bar, and a bar is again 0, so this 0 plus ab bar is simply equal to ab bar. So finally we are left with this, and this is the right choice. Next question: Boolean relation at the output stage y for the following circuit is. So this part consisting diodes, and this is transistor. We have already seen these two parts in the theory. This is OR gate, we can prove this is OR gate, and this part is a NOT gate using transistor. We've already seen this. So this part is NOT gate. So suppose this A and B, if these two A and B give this output at this location, so this Y is simply X bar. So this is a NOT gate. This whole is a NOT gate. We've already seen this thing. Now let us prove this gate is OR gate. So let us make a truth table A, B and X, and in truth table I am taking this let us suppose this is 1 and this is 0. If A is 1, that means this is closed, and if this is closed, so this is 5 and this will become 5, and this will be forward biased. If this is forward biased, so this will be conducting, and this is 5 and this will also be 5 and this is 5. So obviously X is equal to 1, that means X is high. So you can see if any of these two is closed, then this path will be conducting and this will become high. If these two are not closed, that means A is 0, B is 0, then only there is no current here, and if this is 0, so this will also become, X will also become 0. So obviously if this is 0, this is 1, this is again going to be 1, this is 1, this is 1, and this is again 1, both are 0, then only this will be 0. So obviously X is A or B, that is X is equal to A plus B, and we need this X bar here. So A plus B whole bar, and from De Morgan's we can simply write it as A bar B bar. So correct option is option number 3. Next question: the truth table for the circuit given in the figure is. So this is OR gate, and this will give A plus B. This A is coming here and going into this, and this is NAND gate. It will first take the end of A and A plus B, and then we have to put a bar over it. So we can use De Morgan's, and this is A bar plus A plus B whole bar, and again this A bar plus, again we can use De Morgan's, and this is A bar B bar. We can take this as common, so this is A bar 1 plus B bar, and this 1 plus B bar is obviously equal to 1, and finally we will have A bar. So this Y is equal to A bar, so this is A naught, so this operation is A naught. So in the first option A is 0, Y is 1, this is 0, this is 1, this is 1, this is 0, this is 1, this is 0. In this is 0 and this is again 0, so this is not correct. This is 0 and this is 0, this is not correct because Y is A bar. This is 0, this is 1, this is 0, this is 1, and this is 1, and this is not going to be correct. So the correct option is option number 1. Next question: in the given circuit the value of Y is, and we have already given this is 1 and this is 0, so just put and solve it. So if this is 1 and this is passing through this node, so we will have 0 here, and this is 0 and this 0 and this is again 0, these two zeros are passing through this, so 0 and 0 will be 0 and there is a naught on it, so this is going to give 1. So this 1 is going all the way from here, and this 1 is fed into it. So let us proceed from here again. This is 0 and this is fed into this NOT get, so this will give us 1, and 1 is coming from here and here, so this is 1, this is 0, 0 and 1, 0 and 1 will be 0, and not over it will give 1. So this 1 is coming from here, and this is again 1. So this 1 and 1 will be 1, and this is fed into this, and this is not, so y is equal to 0.